Okay. Hello. Oh, sorry. Thank you for the invitation. I'm very nervous. This is my first human brain mapping, so I'm very glad to be here. So, let's get started. Epilepsy is a family of heterogeneous neurological disorders characterized by enduring predisposition to generate epileptic seizures. The most common drug-resistant epilepsy is temporal lobe epilepsy, or TLE, whose seizures initiate in the temporal lobe and occasionally has a characteristic lesion in the hippocampal called hippocampal sclerosis. Due to the hippocampal lesion, temporal lobe epilepsy has been traditionally associated with memory and language impairments. However, recent neuropsychological evidence suggests that impairments are rarely restricted to a specific domain, and many TLE patients do have deficits across multiple domains. As you can see here, these blue ones are just like normal subjects. Then they have some subjects that have deficits in memory, and some other subjects have an overall affection in the cognitive spheres. So multi-domain cognitive impairments have been suggested to be related with, widespread structural abnormalities beyond the temporal lobe, such as in white matter structures and cortical areas, subcortical areas as hippocampi and thalamus as well. So can we relate these cognitive profiles to specific brain networks? We assess this problem by applying unsupervised clustering techniques to neuropsychological assays in order to identify cognitive subtypes in a cohort of TLE patients. And we did some morphological network level structural analysis with MRI. For our design, we have 24 controls, 34 TLE patients, 12 were right, 18 left, and 4 bilateral. They are matched by gender, years of education, all of them adults, native Spanish speakers. They're right-handed with no MRI contraindication and no other neurological comorbidities than the epilepsy. So we use Philips Akiva 3 Tesla. We acquire a high-resolution T1 and 60 direction diffusion-weighted images. We did a full-scale cognitive profiling with Wechsler memory scale and adult intelligence scale. All our participants did all these things. And for the robust classification, we are based on Belek paper for bootstrap analysis of stable clusters. As you can see here, the rows represent each of the subjects, the columns are the cognitive scores, and we took this matrix of cognitive scores. Then we did a bootstrap with replacement, and over the new bootstrap matrix, we did a hierarchical agglomerative clustering, and we obtained the optimal clusterization for this partition. Then we create an adjacency matrix from this. So over the clusterization, we took all the unique values, we sort them, and then we create the matrix, filling it with 1 when 2 subjects are with the same group, and with 0 otherwise. This is a binary matrix, so we did this procedure for 1,000 times in order to obtain a stability matrix, which is represents the subject's probability to belong into the same group. Finally, we got the stable clusterings, and the best partition was for 3 classes in our cohort. And as you can see here, the class 1 has the boundaries between as normal subjects, or the control subjects that are represented in the square. Then class 2 has an overall diminishment in the cognitive scores, and class 3 has a very large affection in all scores. So then we look into the brain structure for each of these classes. So the first thing we measured was the hippocampal volume. This is a percentage of the volume for the subjects. And as you can see, class 1, again, is normal, just like healthy subjects. Then class 2 has some affections, and class 3 has larger affections, as you can see. all these results are sorted ipsilateral to lesion and contralateral to lesion. And here, in the cortical thickness, we see a gradient of changes that where class 1, class 2, and class 3 has increasing changes in the temporal areas and frontal areas with a very big, large effect size. So then we look into the white matter of these subjects, and we can see large cortical and corticothalamic affection measured with fractional anisotropy, and especially in corpus callosum and some other areas. Also, this gradient of changes goes from class 1 that is the same as healthy subject, class 2, and class 3 has more affections. So after this, we create, we wanted to see if the connectome relation to these cognitive profilings. And in order to see this, we create structural connectivity matrices were calculated with diffusion weighted images using anatomical constraint tractography. And we use informed filtered tractograms to correct the anatomical bias. Then we did parcellation of the cortical areas with free surfer and with ball brain for the subcortical areas. After that, we measure the connections as the number of streamlines between two areas to create these matrices. And we perform a network analysis where each node is a structural area and the connection is the streamlines. We measure path length, degree, and cluster coefficient. As a measure of segregation, the clustering coefficient, we found a class-dependent gradual decrease in the node network parameter. And we can see that the local level of connectedness of the network is decreasing from class 1 to class 3. Then when we measure the degree centrality, which is the number of connections to a node, we also see the differences in the frontal areas for class 3, which talk us about decreasing the connectivity. And then finally, the most striking result that we have is the characteristical path length, which is a measure of integration that provides us information about how close a node is connected to all the brain. As we can see, class 1 and class 2 has no many changes, but the sensitivity in class 3 tell us about the global affection that defines this group, having a very long path length. So we came up to see that large connectivity changes are related to small but spread abnormalities through all the brain. So as a summary, our bootstrap-based clustering converged on a 3 subtype solution. Then we found a gradient of structural abnormalities related to the spread damage in temporal lobe epilepsy patients. Then the class 3 had the most severe structural changes with more global and less localized affections. And our network analysis showed the most marked perturbations in class 3. And class 1 has the least abnormalities compared to controls. So that's it. Thank you for inviting me, and thank you to Professor Luis Concha and Professor Boris Bernhardt, and to the labs where I am, and all the sponsors for this project that are a lot. And thank you all for coming here.